Hey, excuse me, hey Algebra 2. Let's talk about identities with trig functions. We're going to start talking about identities with trig functions. Actually, what we're going to do is prove the Pythagorean identity with trig functions. And we're going to start doing that by talking about the Pythagorean Theorem, just regular. So let's talk for just a second. What I've drawn here is a unit circle. Okay, this is not the first time you've seen a unit circle. The equation of this unit circle is x squared plus y squared equals 1. That means the origin is the center and the radius is 1. Okay, so if we talk about theta, which is the angle, I've drawn a triangle here, this triangle. So theta gives us a point on the circle where the hypotenuse has a value of 1, and then we have x sub theta, I have a hard time drawing those, and y sub theta, which represents point P, right? So we have a unit circle, rotating, positive, theta degrees, the coordinates of P are given. So we do know that, x sub theta is the same as cosine theta for the unit circle because our hypotenuse is 1. And y sub theta is the same as sine theta because we're on the unit circle and the hypotenuse is 1. I know you know this, but we have theta. So cosine is adjacent over hypotenuse. Adjacent is your x value, x sub theta. Sine is opposite over hypotenuse. That's your y value, which is y sub theta over 1. Okay, we're going to combine this information to get a formula involving sine and cosine. So we have our Pythagorean theorem. Well, let's just replace these values in the equation of the unit circle by the coordinates of P. So instead of x squared, we're going to have cosine squared. And then instead of y squared, we're going to have sine squared theta, where theta can be any real number. Notice, as a little aside here, to make sure that we're all clear, that we're using, for instance, cosine squared theta. I should parentheses. Cosine squared theta in place of cosine theta squared. Okay, both are correct. This is just a little bit easier to write. Okay, same with sine. Both are correct. Okay, they are equal. You'll never see the second one. This is what we use in math world. So that's what we're sort of doing. So the equation, in fact, another little aside, this is just what we have shown given our equation of a circle. But what you're normally going to see in most math textbooks is sine first. Okay, that's just what you're going to see. This right here is called an identity. So take a note. That's an identity. Okay? All right, so we just did the Pythagorean identity, which was sine squared theta plus cosine squared theta equals 1. Okay, put that one in your back pocket. Now we're going to do another one. Okay, so let's take the Pythagorean identity and divide both sides by cosine squared theta. So I have sine squared theta plus cosine squared theta equals 1. I'm going to divide this side by cosine squared theta and this side by cosine squared theta. Okay, what you see here, I'm going to get, let's just show all the steps. Sine squared theta over cosine squared theta plus cosine squared theta over cosine squared theta equals 1 over cosine squared theta. Simplify. Sine over cosine is tangent. So this right here is actually tangent squared theta plus 1 equals secant squared theta. Right? We now have another identity. We now have two identities. Let's point out some interesting facts with this particular identity. When theta equals negative pi over 2, 3 pi over 2, basically it's pi over 2 plus k pi. We've used that one a lot, right? What happens when we have theta as those values? Well, tan and secant are undefined at those values because you're dividing by 1. Okay, undefined is bad. Cosine of theta is 0 at those values. So we can't divide by 0. So no longer, like with the Pythagorean identity, we can use all values. With the identity we just proved, we can no longer say that we can use all values. It's not true for all real numbers theta. Okay? It doesn't work for, not theta, I'm sorry. Yeah, for all values theta. It does not work for pi over 2 plus k pi, where k is an integer. Okay? So to summarize what I just said, tan squared theta plus 1 equals secant squared theta. That's defined for theta is not equal to pi over 2 plus k pi, where for all integers of k. Let's talk about the range of our identity. Remember, the range is the output. So what is the range? So if we look at the ranges of the functions, it's all real numbers. Okay, the y values can be all real numbers for anything greater than or equal to 1. For both tan squared theta and secant squared theta. Cool. Okay, let's try some exercises with our newfound information. So, recall the Pythagorean identity where theta is any real number. So for sine x, given cosine x equals 3/5, find sine x given cosine x equals 3/5. First time I went to do this problem, I started drawing myself an awesome triangle and saying, okay, if this is x, cosine is adjacent over hypotenuse. Pythagorean theorem makes this side 4. I can go ahead and solve it. That's not what we're going for. So pause on that and let's use our identity to figure it out, because that's what we're here to do, right? That's what we're learning. So our Pythagorean identity says sine squared x plus cosine squared x equals 1. So plug it in. Sine squared x equals, plus 3/5 squared equals 1. I'm doing all the steps. I'm going to skip this one. 1 minus 9 over 25. 1 minus 9 over 25 would be 16 over 25. Luckily, It's a perfect square. I can take the square root of both sides, and sine x equals 4/5, which works with what I drew up there. But what we need to look at is the range they gave us. I usually go back to the unit circle, so I'm going anywhere from negative pi over 2 to 0. Let's see if that works. Here we have sine is your y value, so sine is positive here, positive there, negative and negative. So we actually want to go to, I didn't put that in. When you take the square root of both sides, you have to account for the positive and the negative. So in this example, sine x is going to be the negative value because of the range that they give us and where it goes. There we go. Okay, for this next one, for part B, I'm going to start that on a new slide just to make sure I have enough space. Okay, we have lots of space now. Let's go with the Pythagorean identity again and see how we can make that work for a tangent. So sine squared y plus cosine squared y equals 1. Okay, no problem. So sine squared y equals 1 minus 25 over 169. Sine squared y equals 144. Trust me, works out great. Square root of both sides. Sine y equals plus and minus 12 over 13. Works perfect. Okay, look at the range that we have. So we're sine is positive, positive, negative, negative, and we're looking at all from, so that's wrong. Our range is from pi over 2 to pi, so it's in that range, so we have to go with the positive one. Oops, I have to turn that off. 12 over 13. Sorry about that. Okay, so let's look at tangent y equals sine y over cosine y. We have 12 over 13 over negative 5 over 13. Do the math here. The 13s cancel out. We're at negative 12 over 5 as an answer. Sort of fun. Let's try another one. Write tan z in terms of cosine z for, let's see, we're between pi and 3 pi over 2. So we're in this quadrant here. So let's look at that Pythagorean theorem, Pythagorean identity again. Write it in terms of cosine z. So let's go ahead and solve for cosine. Write tan z in terms of cosine z. Nope, let's do this. Sine squared z, it's going to be sort of magic. 1 minus cosine squared z. Square root of both sides. Sine squared z equals the square root 1 minus cosine squared z. And here we've got positive, positive, negative, and negative for sine. So let me correct a few of my errors here. That would be sine. And here we want to make sure that we are dealing with the negative one, right? So don't forget your little negative sign. But because tan z equals sine z over cosine z, we now know tan z equals negative 1 minus cosine squared z over cosine z. That was fun. I mean, I would look at these as sort of when we first started learning about equations and actually no, formulas and rearranging formulas in terms of other values. It's sort of what we did where you're trying to isolate certain values and making your identities look different even though they're the same. Let's try number 2. Use the Pythagorean identity to do the following. Rewrite the expression cosine theta sine squared theta minus cosine theta in terms of a single trig function. State the resulting identity. When I look at that, I see that I can factor something out, which is pretty cool. I'm going to factor, I mean, it's almost like we have x, y squared minus x. You see that? So I can factor an x out. And I would have x, y squared minus 1. That's what we're going to start doing on this problem. So this term has a cosine and this term has a cosine. So I'm going to take the cosine theta and factor it out, and I'm left with sine squared theta minus 1. And that right there is our Pythagorean identity. Sine squared plus cosine squared equals 1. We have cosine squared equals 1 minus sine squared. And if I do negative if I multiply both sides by -1, I would get sine squared, hard to read that, minus 1. You see my little notes that I have over there? I just want to make sure that you see it. So I factored the cosine squared out. Now I can replace this with negative cosine squared theta because of what I showed you over here with my little notation, which I hope makes sense. So what I have left is cosine of theta times negative cosine squared of theta, which gives me, that's sort of hard to read over there. There we go. Negative cosine cubed theta. That's sort of fun. So there's my answer. Okay, the beginning equation in terms of just a cosine. Okay, let's try another one. Rewrite the expression 1 minus cosine squared cosecant in terms of a single trig function. Okay, I'm going to take that single trig function with my little notation, sine squared plus cosine squared equals 1. Sine squared equals 1 minus cosine squared. So it looks like if I can isolate, like this piece right here, I can replace it with sine squared theta. Sine squared theta times cosecant theta. And what is cosecant? Oh, I have a typo there. Cosecant is really 1 over sine, right? So I have sine squared theta times 1 over sine theta. This cancels and my squared cancels, so I'm left with just plain old sine theta with parentheses. That was fun. Okay, part C. This is a really interesting problem. We're going to do a lot of practicing of manipulating equations to get the equations to sort of show us what we want to show. This one says find all solutions to the equation 2 sine squared theta equals 2 plus cosine theta in a given interval. I'm just going to give you a little example here. If I gave you the equation, oh goodness, sorry, 2x squared equals 2 plus y, and I told you to give me all of the solutions, you guys would like, oh, okay, I'm just going to say, okay, y equals 2x squared, let's see, if I moved that over, minus 2, I'd factor out a 2, and you get x squared minus 1. And then you're like, well, that's a difference of two squares, x plus 1, x minus 1. You could say that, okay, x is going to be equal to plus or minus 1. Okay, if I told you to solve it, like that's what you may or may not do. Notice I just ignored this y. I set it equal to 0 after the first step. It was just an example of what I'm asking you to do with a problem like this. Because these are a little bit difficult, but I've always thought they were fun. So let me erase this big old mess right here. I know there's easier ways to erase, but now you can just listen to my voice as I erase. It's okay. Get all the pieces and parts off. I think I got them all. So let's start working with this problem. I have 2 sine squared theta equals 2 plus cosine theta. I'm going to change this sine squared theta to be in terms of cosine so that I have all the same. Because you remember the example I gave you, which was like 2x squared equals 2 plus y. I had x's and y's. It's not good to have x's and y's. You want all x's or all y's, not both. So let's change this into a cosine. So 2 sine squared theta is 1 minus cosine squared theta equals 2 plus cosine theta. Cool? Let's see what else we can do. I'm going to distribute that through 2 minus 2 cosine squared theta equals 2 plus cosine theta. Now I can cancel those out, and I'm left with 0 equals, I'm moving the cosine squared to the other side, so cosine theta, and I'm actually going to write it first because I like my squared things to be written first. It makes me feel comfortable. 2 cosine squared theta plus cosine theta. So now we have something that looks almost like this. 2x squared plus x. What are we going to factor out? Well, I can factor out an x, or in our case, a cosine. Cosine theta times 2 cosine theta plus 1 equals 0. Sorry, I'm just going to relate it back to this one. So I just did x, 2x plus 1. Now if we're solving an equation, we can say, okay, x equals 0 or x equals negative 1/2, right? Well, it's the same over here. Okay, so cosine of theta equals 0 or cosine of theta equals negative 1/2. We just solved it. You guys did it. Now let's look at the unit circle. Are you proud of yourselves? I'm proud of you. So there's our unit circle. At what points on this unit circle is cosine theta equal to 0? Well, cosine is your x value, so let's start this one. We're going to do it in red. Cosine theta equals 0 at pi over 2 and 3 pi over 2. Okay, so cosine theta equals 0 if theta equals pi over 2 or 3 pi over 2. Notice we're just in that range. Okay, all right, now let's look at the other one. We're going to do that in blue. Cosine theta equals negative 1/2. Okay, cosine is x, so x is negative over here. So somewhere over there. So 1/2, that's our 30, 60, 90 triangle. So cosine, I need another picture. This is 2, that's 1, that's square root of 3. I got loud there for a minute. So cosine of theta would be adjacent over hypotenuse, and that is a 60-degree angle. So where in my unit circle do I have 60-degree angles? If this is 60, we're at, what is our radians there? That is 2 pi over 3. Okay. Yep, because that would give us 120. So that's 60 degrees. That would give us a negative 1/2. So theta equals 2 pi over 3. Okay, we can also get the angle down here, right? So if I do 120 degrees plus 60 will get me 180, plus 60 again will get me in the right spot. That is 240 degrees, which is also 4 pi over 3. So that would get me over there. And that is also negative 1/2. So we have all of our answers. Need to find a fun color. There we go. This would work. The solutions of the equations are pi over 2, 3 pi over 2, 2 pi over 3, and 4 pi over 3. I thought that was tons of fun. Hopefully you agree. All right, let's go through these. Which of the following statements are identities? If a statement is an identity, specify the values of x where the equation holds. First of all, we have sine x plus 2 pi equals sine x. That is an identity, so for any value of x, we have sine x plus 2 pi is going to be equal to sine x. If you just look at the unit circle, we have sine x plus 2 pi, we get back to the beginning, plus 2 pi, etc. Excuse me, sorry about that. Let me repaste this word, so for any value. And this is defined for all real numbers. All right, let's look at secant x equals 1. I got rid of c. We're going to move it to the next slide because I needed a little more space. This is not an identity. If we just plug some values in for secant and test, so basically, whatever we put in for x, does that equal that? If we look at secant of 0, we get 1. If we look at secant of, I don't know, pi over 4 is an easy one, we get the square root of 2. Therefore, not an identity. And the instructions say, if the statement is an identity, specify the values of x where the equation holds. So it's not an identity. We can be done. All right, let's look at sine of negative x equals sine of x. Again, try a few values out. If we look at, I don't know, sine of negative 1, I get negative 0.84 and some rounding, and then sine of 1, I get positive 0.84. So not an identity. This would actually only been true. The only time that it is true is when sine is 0, because negative 0 is still 0. Okay, look at letter D. This is an identity. We actually proved this identity as part of our lesson. So, yes. And it is defined as long as we don't have an undefined part of the equation. So theta cannot equal pi over 2 plus k pi. That was part of our, when we found the identity, when we proved it, this was part of our answer. Very cool. Next one, sine of pi over 2 minus x equals cosine x, where the functions are both defined. This does work. Sine of pi over 2 minus x and cosine of x. If we look at the unit circle, that brings us up to this point for both of them. So it works for any value. If we do x equals 0, that would give me sine of pi over 2 and cosine of 0 have 1 and sine of, I think my calculator's in degrees. Nope. Sorry, sine of, you hear me typing. Yep, sine of pi over 2 equals 1. I was in radians. It works for any values of x. We can keep on plugging some in as long as we get 1 equals 1. Life is grand. And this would be an identity for all real numbers, no matter what we're doing. How about sine squared x and tangent squared x? That's not an identity. Really, the fact that this is sine squared x over cosine squared x tells us that we're not going to be defined for a few values. That gives us some issues. And yeah, really this means we have sine squared x equals sine squared x over cosine squared x, which that tells me it's not an identity. Okay, I've got an extra cosine squared x in there, so it doesn't work. Cool. In closing, we have our identity, the one that the book is reminding us of, and the other one that we did. This would be where theta can't be pi over 2 plus k pi for all integers of k. Cool? All right, let's do your problem set. Good work today.